All right, welcome to the screencast for the first screencast for the stoichiometry unit. This is our last unit in terms of material that we will be covering in this class. So let's just go ahead and get started. So this is Unit 9, Stoichiometry. There is a video linked to this. We will watch it in class, so don't worry about doing this. This will just be the first thing that we do in class. So the point of this is we're going to draw connections between our balanced equations and what happens in the lab. Or what actually happens in a chemical reaction. So you can see this balanced equation, but we're going to see how we can manipulate these equations and how we can predict how much products or how much reactants we need or how much we're going to make in a reaction. That's the whole purpose of doing this. So the first two objectives just go through what a mole is, because you have to understand what a mole is before we can do stoichiometry. So describe methods of measuring the amount of something, and define Avogadro's number as it relates to a mole of a substance. So our essential question is, why is the mole important and how do we use it? So basic measurements, just what is a mole? It is nothing more than a simple measurement. It's a way to count very small things like atoms. These are other measurements that you should be familiar with. A dozen means 12. A couple means 2. Score means 20, so if I said I had a score of this, I would have 20 of anything. A gross means 144 of anything. The term mole just means I have 6.022 times 10 to the 23rd of anything. It's a huge number. And the reason we work with that big of a number is because atoms are so small that even if I had 1 mole, which is that many atoms, it wouldn't take up very much room. So the mole, Avogadro's number, is 6.022 times 10 to the 23rd of anything. So 1 mole of magnesium atoms is 6.022 times 10 to the 23rd atoms. A mole of sulfur atoms is 6.022 times 10 to the 23rd atoms. A mole of people is 6.022 times 10 to the 23rd people. A mole of pencils would be 6.022 times 10 to the 23rd pencils. So it's just a measurement. These are 2 lab activities here that I don't know if we're going to have time for necessarily in class. If we do, we'll go ahead and do them. But if not, it's not that critical that we complete both of these labs. I'm going to play this video clip for you right now so you can watch this as part of this screencast. And the summary format for objectives 1 and 2 is a 3-2-1 summary. It's going to be kind of hard to write that much, so don't feel bad if you cannot write 3 things that you learned, or because there's not much to this objective. So here's the video as soon as this loads. That kind of explains a little bit more in depth what a mole is.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amedeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is... anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay, so a little explanation into what a mole is. I'm going to go ahead and stop here, and objective number 3 is also going to be part of this on the same due date or due the same day, but I'm going to do it as a separate screencast.